Boolean representation of ands, of ors. Given a Boolean representation, can you tell whether it's linearly separable or not? Any guesses? Or any other representation. Can you think of a representation under which you can tell if it's linearly separable or not? So when I give a Boolean representation, the implicit assumption is that it's a function of Boolean inputs. It doesn't have to be. You can talk about linearly separable function in a continuous space of inputs. But in this case, it's the Boolean space of inputs, so this is a function defined on the vertices of a hypercube. Okay, so in 2 dimensions, if you have only x1, x2, really all you care about is 4 points. 0, 0, 0, 1, 1, 0, and 1, 1. Or you can call them by different names. -1, +1. If the origin is here, then it's -1, -1, -1, +1, +1, -1, +1, +1. If it's 3 dimension, then you can literally think about it as a cube. And you have 8 vertices corresponding to 0, 0, 0, 0, 0, 1, 0, 1, 0, and so forth, all the way to 1, 1, 1. In the general n-dimensional case, the hypercube has 2 to the n vertices. Each vertex corresponds to one possible input, one possible combination of the n binary inputs. And the question is the same: can you pass, once you label these with positive or negative, say yes, no, 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 yes, no, yes, no. Is it possible to pass a hyperplane? In this case, since n is 3, the hyperplane would be of dimension 2. Is it possible to pass a 2-dimensional plane that would separate all the s's from all the no's? That's what a threshold function would do. Back to my question. If you're given a function explicitly in some kind of a representation, can you tell whether it's linearly separable or not? It's okay to guess, it's okay to, yeah.
This is just a thought that you could try listing out every single possible input and their output and see, just writing down the equation and see if there's some kind of conflict.
Yes. Well, you can go even further than that, so that's good. You can write these as a set of equations. So there are 1 through m possible inputs. You write down all the possible inputs and you know what the output should be. So you're saying f of x is yes, f of this is saying no, yes, yes, no, whatever the values should be, right? You can calculate, whatever the representation, you can calculate what value the function is assigning to every possible input, and then you know that the function is supposed to be a linear weighing. So it's a w dot x1 is this, and here it's w dot xm. So now you have a series of m equations with n variables. The n variables are the w's. Actually n plus 1 for w0. Right? The problem is that m is 2 to the n. For the full description of the function, there are 2 to the n possible inputs. So you have 2 to the n functions of n plus 1 variables, and you can try to solve it, and if there is a solution you say yep, it's linearly separable, and if there's no solution you say no, and that's fine. That's a completely legitimate decision function. The only problem is that it's exponential in n. So if you were given the function explicitly as its set of values over all 2 to the n possible inputs, then the solution is only polynomial in that. But that is exponential in n. So in practice, for any reasonably large value of n, this is computationally very hard to do. Now, your original suggestion is to write it down and to look for conflicts. And you might be able to find conflicts right away. So there are situations where you can tell, no, this is not linearly separable. But that's not guaranteed to always work.
Shouldn't you threshold the equation?
I'm sorry?
Shouldn't you threshold the equations? You want to check linear probability.
Threshold the equations.
W is
At a threshold, you mean?
yeah.
Well, I've assumed that W starts from 0, and W0 is the negative threshold.
It should be whether it's larger than 0 or smaller than 0. Why yes and no are only 1 and 0?
You mean it should be an inequality rather than an equality?
Yeah.
Yes, you're quite right. It should be an inequality, not an equal. So this should be greater than 0. Is that what you meant? And it should be less than 0. Thank you. So it introduces a slight complication because it's hard to work with inequalities. But you can assume that if it's greater than 0 or less than 0, that there's a margin around 0 to stay away from. And you can always achieve that by multiplying all the weights by a constant. So yes, it's a little more complicated than I said. Thank you. It's a system of inequalities rather than inequalities. Nonetheless, the answer is the same. We don't know of any tractable way of answering that question, of being guaranteed an answer to that question. There are many tests that will tell you when it's not linearly separable. So I can give you various properties of linearly separable functions. For example, they're all monotonic in each one of their variables. I'll explain what I mean by that. For a function to be monotonic in a variable, it means that as this variable goes, say, from 0 to 1, the value of the function always increases or stays the same, but never decreases. That's to be monotonically, or positive monotonic, or increasing monotonic. Okay? You can also be negatively monotonic, or monotonically decreasing, if whenever the value of the variable goes up, the value of the function stays the same or goes down. Okay? The function must be either monotonically increasing or monotonically decreasing in any one of its variables. It could be monotonically increasing in some of them and monotonically decreasing in others. But for each one of them, it has to be either or. It's kind of easy to see because if it is a linearly separable function, it can be implemented as a perceptron, which means there is a weight that connects that input to the function. So if the weight is positive, you would guess that the function is monotonically increasing in this variable. And if the weight is negative, the function is monotonically decreasing in this variable. So if you see a function and you can find either by example or by inspecting the representation of the function that it is not monotonically increasing in one of its variables, is not monotonic in one of its variables, then you know it's not linearly separable. The classic example is x1 XOR x2. I'll find you an example when it's not monotonic in x1. So for example, when x1 is 0 and x2 is 1, the function is 1, right? Now, everything else stays the same. This must remain the same. This changes from 0 to 1. The function changes from 1 to 0. Right? So this is an example of why the function is not monotonically increasing in x1. Now, if I change these to 0, I will show you that it's not monotonically decreasing either. So the definition of monotonic is that all the other variables are fixed at some value. And no matter what value they're fixed at, the dependence of the function on this particular variable always goes in one direction. Doesn't reverse direction. So this is a necessary condition for being a linearly separable function. There are actually other necessary conditions that are stronger, or rather you could say weaker, that even if you pass this one, you may not pass the next one. So you need to be monotonic not only in any one variable, but in any subset of the variables. So the definition is quite similar, but not exactly the same. Linearly separable functions also go by the name threshold functions, and also go by the name majority functions. They were all the rage in the 60s when physicists and electrical engineers tried to prove everything they could about their properties and what they can do. If you restrict your attention to binary functions, you could ask, how many binary functions are there of n variables that are linearly separable? How many binary functions are there of n variables, period? That you should know. N binary variables. N binary variables. How many functions? Somebody else, please. 2 to the 2 to the n. How many of these are threshold functions or linearly separable? A majority, a minority, half, 1/n. Anybody wants to guess? 2 to the n? We're pretty close. I don't expect anybody to guess any closer than that, so I'll give you the answer. It's about 2 to the n squared. So it is an exponential number, exponentially n, no question. But it is exponentially smaller than the full number. So the exact theorem says that the number of threshold functions in the limit as n goes to infinity, well, if you take that and divide it by 2 to the n squared, you get something that's between 1 and half. So basically, this is not meant to be a small o, I'm sorry. This is a regular big O. Which means that if you take any reasonable value of n, 20, 30, and you choose a function at random, it is extremely, extremely unlikely that it is linearly separable. I want to give you one other tidbit about linearly separable functions. Our common intuition of linear separability is that functions are monotonic in their variables. But as I pointed out to you, monotonicity in variables is a necessary but not sufficient condition. I want to give you the smallest known example of a function that is very monotonic in all of its variables and is still not linearly separable. And once I give it to you, you will see very clearly, very easily, why it is not linearly separable. And the function is very simple. It's x1 and x2, or x3 and x4. W1, W2, W3, W4. First of all, it's very clear that it's monotonically increasing in all four variables. Right? It can only benefit from these becoming positive, or going from 0 to 1. So the weights are all positive. Now what does it take for this function to exceed the threshold? Let's say a threshold of 0 or whatever. Some combination of these two or combination of these two. But you should be able to prove, and maybe it's in your homework and maybe we'll put it in your homework, that actually there's no way of selecting the weight such as this is true. And the reason is the crosstalk between them What if x1 is 2 and x3 is true, but the other two are not? I don't want to give you too much, but think about it a little bit. It's a very simple function. So if it's 1, 1, 0, 0, the function should say yes. And if it's 0, 0, 1, 1, the function should say yes. But if it's 0, 1, 1, 0, it should not say yes. And that's impossible to achieve with weights. Okay, so let's go back to neural networks. So we talked about threshold functions, or linear separable functions, or perceptrons. And the last thing I think we talked about was a network of perceptrons. What do you gain by having a network of perceptrons? What do you gain in terms of representational power? Did we reach a conclusion? What can you represent with a network of perceptrons? Sorry? Boolean functions. Which Boolean functions can you represent? Okay, so you have n inputs. You're allowed to build any network, and let's say for simplicity you have a single output. Can you represent any Boolean function? Are you saying yes?
Yes.
Okay, why?
Because you can combine and or not to form anything you want.
Yeah, you can build any Boolean function by combinations of AND and OR and NOT, and we can do all of these with perceptrons. So a network of perceptrons is a universal approximator of Boolean functions. It turns out you can do it even with a single intermediate layer. So we didn't talk about the depth or size of the network, but you can, if you have the output here and any n inputs here, you can implement any Boolean function with a single layer of intermediate units, which we sometimes call hidden units, for reasons I will explain later. This is a hidden layer. Don't worry about it's called hidden now, just call it the intermediate layer. This is the input, this is the output. Each of these represents a perceptron, and so does this one. Can you think of a quick way of proving this? Of taking any function and representing it in a network with a single intermediate layer? It's along the lines of what you said. Any Boolean function can be represented as an OR of n's. Basically, it's an OR of all the input combinations that result in the positive value of the function. So it could be x1 and x3 and x5, x7, or x1, x3, x7, x14, or, and you basically list all combinations of inputs that make it true. And then each one of these intermediate units represents one of these ORs. We know how to do an OR with the perceptron. So this one will be connected to x1, x3, x5, x7. This one will be connected to x1, x3, x7, x14. Be connected selectively to whoever they need to be connected to, including if you have a negative here, then that would be a negative weight. And then this would represent an OR, a multi-way OR, which we know how to do. So this is an OR, and all of these are ANDs. We know how to build each one of these, therefore we can represent any function. The caveat, or the catch is, what is the catch? It looks too good to be true, doesn't it? Any function can be represented. Please?
There has to be a lot of weights.
There have to be a lot of, not just weights, but units. How many is a lot? I don't mean 7 or 15, I mean in computer science terminology. How many is a lot? Exponential. The number of units here could be exponential. So the good news is it doesn't have to be very deep, but it could be exponentially wide, which is not great. Okay, there's an extension of this to continuous functions. Any continuous function can be implemented or represented by, well, it has to be approximated by a network of this type, where you don't apply the threshold here, obviously, because then you don't have a continuous function. But you can represent any continuous function by a network of just one or two intermediate layers. But again, you need an exponential number of units. You know. So networks of perceptrons are universal approximators. You can think it's good, you can think it's bad. Remember, we said that having a bias is not always bad. Now, is there a hard bias in these kind of networks? Well, if you have no restriction on the topology, namely how many units and how they're connected, then you can say there is no hard bias because anything can be represented. But if you say let's restrict ourselves to small size networks, then you're imposing some bias, and then it's fair to ask what kind of bias, what kind of functions can be represented by a small network and which cannot. Very similar to decision trees. If you can build a decision tree with no limits, then you can represent anything. But if you restrict yourself to small trees, then it's reasonable to ask what functions can be represented, which are not. And not surprisingly, the answer is different for decision trees than it is for neural networks. It's not easy to capture, to characterize the answer, but we all have an intuition of what decision trees are good at. They make individual decisions based on individual attributes. Neural networks, on the other hand, make global decisions based on a weighted combination of possibly all the inputs. Okay, what about learning? Learning a network of perceptrons. So by learning, I mean you have a set of training examples, and let's say you have let's say you have no limit on the size of the network. Can you come up, this is the search problem, can you come up with a network that implements the training examples? Did I tell you that when I ask you a question, it could be an incredibly trivial question, or it could be an open-ended, nobody knows the answer question, and I will try to not let you know which is which? Okay. So let's go back to my question. You have a finite set of training examples. You need to find a network of any size that is consistent with that. Can you do that? And if so, can you do it in a reasonable time? Did you say yes?
Yeah, we can.
Yes. How would you do it?
Because it's going to represent all the training examples. They're anyway going to be represented in the space.
I'm sorry, say the last part again?
No, all the training examples will be, we're going to consider the entire space together. So I think we can represent training examples.
We can represent any, but can you effectively find a particular network? Draw it and draw the weights and calculate the weights and the thresholds that will be consistent with a finite set of examples. Please.
Perfectly consistent, or just
well, if it's a binary function, perfectly consistent. If it's a continuous function, to some approximation.
Well, the binary function here in the set that
Yes, it's right here on the board. Thank you. Thank you. Yes, the answer is absolutely yes. And just draw. What I gave you here was, I'm sorry, yeah, I was here, was how to do it for a fully specified function. But you can do it for a finite number of examples. Each one of these would correspond to one particular example, and then you have to worry about what to do with the negative examples. But yes, you can do that. What you do with the negative examples is you still get the end, and then you make this knot by, say, reversing, putting a large negative weight here, large enough to make sure that whenever this is on, the whole function gets turned off. Now my question is, can you do that if I restrict you to a small network? I give you 10,000 training examples, be they binary or continuous, and I give you only have 100 perceptrons. Go ahead and arrange them in a way and connect them in a way that would implement it. Can you then, do you have an efficient way of finding such a network if it exists, or coming back to me and saying it doesn't exist?
If you give me a binary function, then I could minimize it and try to build it, and that way I can tell you whether it can be represented with the number of perceptrons.
I'm not giving you a binary function, I'm giving you 10,000 training examples. I'm sorry?
And probably the answer is no.
Probably the answer is no. At least we don't know how to do it. I think it's an intractable problem. Okay. Alright, so, and then we said, okay, let's try to do it the way we did it with a linear network by gradient descent. And somebody pointed out that you can't do gradient descent because the transfer function is not differentiable, because it's not continuous. Okay? So let's summarize our findings to date. One linear unit How do I do it? I'll do it like this. This is going to be representation. And this is going to be learning. So one linear unit can represent all linear functions. And therefore, in learning it is easy, very easy. If you remember, you can solve a system of linear equations, or you can do gradient descent because the error surface is convex. Network of linear functions. Linear units. Unfortunately, it's the same thing. So this is kind of disappointing, and therefore this is too. This is good. This is not relevant. Why should we go for a network if we could do it with one unit? Perceptron. To remind you, perceptron is this thing, whereas the linear unit is this. Oopsie, this thing. Perceptron. All linearly separable functions or decision surfaces, or let's call it functions. So this is kind of disappointing too, because we don't like to represent only linear stuff. Linear stuff is for sissies. Learning is a mixed story. Yes, we can learn it, but only if there is a solution. And we can't tell if there is a solution or not until we find one. Yes, it's the perceptron learning rule or theorem, but undecidable. I shouldn't say undecidable. It's because it is decidable in exponential time. It's just not decidable in polynomial time. So, what should I say? Yes, but only if one exists. Okay? And if it doesn't exist, we will never know. Never unless we wait exponential time. Okay, now we have a network of perceptrons. And what do we got here? Everything. So now we're happy. Here we're happy. But we don't have an effective way of learning a compact network. No effective way to learn. Because not differentiable. So what we're kind of playing a game between, we want a large representation power, but we want to be learnable. And we haven't gotten there yet. When we move to a large representation power by introducing nonlinearity of the step function, we lost the ability to learn effectively because we cannot do gradient descent and we can't solve it algebraically either. Now I'll go back to the comment I got last lecture. Somebody suggested a solution and I ask you to hold it back. Is it yours? Okay.
Continuous approximation to step function.
Okay, so this is our solution. We're going to have a continuous approximation to the step function. It would retain the nonlinearity so that the expressive power is large, the representation power is large, but it would be continuous so that the error function is continuous so that we can take the derivative so that we can do gradient descent. Okay? That's our solution. So what we're going to do is introduce a function that approximates this. And how do you approximate this? Well, continuously, well, you do something like this. Right? Familiar with this function? It's called a sigmoid. Sigmoid function. It's a continuous and differentiable approximation of the step function. It's our transfer function, right? It's this thing, transfers the net. And the definition of a sigmoid, the mathematical definition of sigmoid of net, is 1 over 1 plus e to the negative net. And there are other ways of parameterizing it, but this is the very simple way of parameterizing. So when the total net is extremely negative, negative infinity, the negative net becomes very large, positive, goes to infinity. E to the infinity is infinity. 1 over infinity is 0. So as this goes towards infinity, towards negative infinity, it hits the 0 point here. And the other extreme, when the net is very, very large, negative net is e to a very negative number, which is 0. 1 plus 0 is 1. 1 over 1 is 1. So the asymptote here is 1. And when net is 0, e to the negative 0 is 1. 1 plus 1 is 2. 1 over 2 is half. So the crossover point is half. So it's a symmetric function. Now the full sigmoid function actually has several other parameters. You can control separately where the minimum is, where the maximum is, and 2 other parameters. One is the slope here. Do we hit it like this or do we hit it like that? Or like this? And another parameter that controls is the overall shift, where the halfway point is reached. In our very special case, the minimum is 0, the maximum is 1, the halfway point is reached at x equals 0. But we can still control the slope here by introducing a weight here. So if you vary the weight here in front of the exponent, the function varies from being extremely close to step function. If the weight here is very large, it is extremely close to step function. If the weight here is very, very small, very close to 0, this could become something like this. Very smoothly changing, almost linear. But not completely linear because it has to asymptote here and has to asymptote there. So you can make the step as hard as you want. Now in the case of a neuron implementation, the weight here is effectively controlled by multiplying all the weights that come in by a constant. So if you multiply all the weights by a constant, by a large constant, you're making that step function sharper. All the results that I told you about with regard to perceptrons hold here too. Namely, a network of sigmoid units is a universal approximator. It can approximate any function. It can approximate any continuous function with just a single intermediate layer. It can even approximate non-continuous functions, but it needs 2 intermediate layers for that. The catch is that it may need an exponential number of units of neurons in that layer. So I'll skip the single sigmoid and I'll just talk about network of sigmoids. Network of sigmoid units. Everything. In principle, everything. Namely, with a large enough network, there's everything. And what about learnability? Now, the transfer function is differentiable. The summation function has always been differentiable. It's just an inner product. Therefore, the entire calculation of a sigmoid unit is differentiable. And a whole network consists of, what's the mathematical word for it? Composition of sigmoid units on top of other sigmoid units, because the output of some sigmoid becomes the input of another sigmoid, and therefore the entire computation of the entire network is one big differentiable function. It's a differentiable function of the inputs, but even more importantly, it's a differentiable function of the weights. Why is it more important that it's a differentiable function of the weights? Because it's the weights that we're going to be modifying as we do our learning. So if you represent the output of some network of sigmoids, this is a function of x1 through xn, but also of w1 through wm, where the number of weights can be very large. This is the combined all the weights in the network, the weights from all the intermediate units and all the other units and all the thresholds. You can think about it as a function of all these things. Once you fix the weights, you fix the network completely, and then it becomes just a function of the inputs. But you can also think about it as a function of the weights. The important thing is that this is differentiable in all of its arguments. So all we need to do now to learn a network from examples is we're going to fix the topology. And it's a good question of what topology to choose, but suppose we have some fixed topology. Namely, we know how many inputs, we know how many other layers. If it is layered, if it's not layered, we know the exact connectivity. Now we take our training examples and we perform gradient descent. How do we perform the gradient descent? We start by defining an error function. Okay, so this is the general recipe. Here, let's say that's the network we're trying to learn. This is the topology, it's fixed. We define error function. The error function is always with regard to a specific training set and specific topology, and the error function would be written as sum over all the training examples. How many training examples? Let's say K. What do we usually use for training examples? M? I don't know. I want to use D because I think that's what the book and the slides use. And now we are looking at the error of each individual training item. And the training item would be the teaching signal or the target signal, T sub D, minus the actual output of the network. This is the output of the entire network for input D squared. Let's put a half here because we know we'll need it. Doesn't matter what constant we put here, right? This is our error function. Now what is it a function of? After we summed explicitly over all our training examples, it remains only a function of weights. That's important. It's only a function of the weights. Now when I put the weight vector here, what I have in mind is all the weights of all the units and all the thresholds. This is a differentiable function of the weights. And now imagine the space, the Cartesian space of what's called the weight space. Suppose you have 100 units in your network, and they each have on average 15 weights coming in. So you have a total 15 weights plus the threshold at 16 times 100, you have a total of 1600 weights in the network. Imagine the Euclidean space of 1600 dimensions. Every point in that space corresponds to a particular value of all the weights in the network. So it corresponds to a particular function that the network computes. Right? As you move that point in some direction, you change some or all of the weights. As you change the weights, what the network computes, the function network computes, changes. Now imagine that space is also annotated with the error of each point. A point corresponds to a particular set of weights, corresponds to a particular function, corresponds to a particular error. Now we're searching that space for the place with the lowest error. Unlike the case with a linear unit, it is not guaranteed to be a convex function. So there could be lots of local minima, and we're sure to find one of them. How are we going to search the space? The gradient descent algorithm says that we calculate the gradient of the error with regard to the weights, and then we take a small step in the direction of this gradient. This is our eta, and we call that the change in weight. This is a one-line description of the gradient descent algorithm in vector calculus notation. If you're not comfortable with vector calculus notation, I can write it to you for you in terms of each individual weight. Let's index all the weights. So this should be negative here because we want to go down the gradient. Gradient is defined as a direction of going up. We want to go down. We want the minimum error, so we want to go against the gradient. If I index all the weights in my network, of which there are, we said 1600, and typically in a real network you would have hundreds of thousands. If I index them all by I, the change in weight I that I introduce at the current step would be negative eta times the partial derivative of the error with regard to weight I. What this upside down triangle does is just a compact notation for a vector of all the partial derivatives with regard to W1, W2, W3, all the way to W1600. So this is the weight by weight formula for gradient descent. I gave you now the conceptual framework for gradient descent. There is still a lot of algebra, still a lot of low-level manipulation that we need to do to turn this into an actual algorithm. Because this is always true. And then I argued with you that for you that in the case of a network of sigmoid units, this is in principle differentiable. And if it is differentiable, this partial derivative exists. But I didn't show you what that partial derivative is. And it turns out it's not trivial to calculate the partial derivative. It is trivial to calculate it for a single sigmoid, but not for a network of sigmoids. So the main progress that came, that sort of breakthrough that allowed this to become useful, came somewhere in the 80s, where somebody derived a simple recursive formula for this expression, partial derivative of a network of sigmoid units with regard to a weight. It turns out actually it was calculated before in the 70s, but nobody paid much attention because of the problem of local minima. It was known that neural networks can be universal approximators. Neural networks, from now on when I say neural networks, I'll talk about sigmoid units because they are the most commonly used kind. It was known that they are universal approximators. It was known that they are differentiable and that you could do gradient descent in principle. But the common wisdom was that they'll get stuck in the local minimum, and what did you get out of it? Sometimes in the 80s, a group of people, including Jeff Hinton, who was, I don't think he was at CMU then, but he came to CMU after that, showed several things. A, they resurrected the formula for the recursive calculation of this, so that made it popular. And the second thing is they applied it to a set of interesting problems, non-trivial problems, and showed that yes, we have not solved the global minimum, local minimum problem. It is a theoretical weakness, but in practice it doesn't get much in the way. Many problems you can find a very decent local minimum for. This happened in the mid-80s, and as a result, the following decade there was an explosion of neural network research, and basically it boiled down to 1 million people taking their favorite problem and throwing a neural network at it, and often surprised that it did quite well. So this was sort of a very common thing to do at a time, and it did prove quite useful. I'd say neural networks are like the first success story of machine learning, in that here you have a universal approximator, a representation that can, in principle, represent any function, a very simple algorithm, which I'll show you in a minute, that you could either write yourself or download. Well, there was no web then, but you can get it easily by email. And you can do gradient descent and find a solution that often was a decent solution. It was so easy that it was also easy to abuse. It is so easy, and you don't have to understand machine learning, and don't have to understand bias, and don't have to understand lots of things. You can do it without much understanding, which is really the curse, because it was indeed abused many times. We'll get to that. But for now we're in the happy mode. It's a big success story. It's a general vanilla tool that you can throw at anything. So the specific method of calculating the partial derivative with regard to every weight is called the backpropagation algorithm. And I'll describe it to you, and I'll tell you why it's called backpropagation. But for you just to appreciate the difficulty, remember that a network has many layers. They don't have all to be the same depth and so forth, but you can kind of understand how calculating the error with regard to this weight would work if it's this weight, because this weight only participates in the total output through its influence on the sigmoid function here, right? There's summation and then sigmoid. But how do you calculate the derivative of the error with regard to, say, this weight? It's a very indirect effect. The function is differentiable in principle with regard to all of these weights, but finding the actual dependency is hard. And the essence of the backpropagation algorithm is to define a quantity called the error signal. And the error signal is first defined at the top, and then is recursively pushed down, recalculated for every neuron further down the chain. This is why the algorithm is called backpropagation. You backpropagate the error signal, and then given the error signal, you can calculate the actual derivative of the error. So all this is kind of details. It's a detail of the calculus. You can think about it as a problem in calculus. It's really not a problem in machine learning. It's a problem in calculus. Machine learning stopped when you chose the transfer function, you chose the topology, you realize that you have in your hands a universal approximator. It's only universal if you didn't fix the topology. But you fix the topology, it's a decent approximator. You have training examples, and you chose the method of learning, which is gradient descent. Once you wrote down this formula and this description, the machine learning part is over. Now it's just calculus. But nonetheless, I need to show you the calculus. So let's do that now. One more point. Sigmoid is not the only way to approximate a step function. As you can imagine, there can be many other functions that look kind of like that. They're not exactly the same. For example, arctangent. You know, a tangent looks like this. So if you turn it 45 degrees, which is what you get with an arc inverse tangent, it goes like this. Arctangent and sigmoid are not exactly the same function, but they are surprisingly similar in that if you set the parameters right, they deviate by no more than 2% from one another. So you could use arctangent, and then the function would look a little bit different, the derivatives would look a little bit different, and it would work fine too. You can define any function that you want to be an approximator of a step function. In fact, you don't even have to look at a step function. It could be a two-step function, it could be something else. As long as it's non-linear, it'll do interesting stuff. One could argue it should be monotonically increasing, otherwise some bad things would happen. But let's stick with something that looks like a step function. Why did they choose a sigmoid function? And the answer is that its derivative has a very simple form, simpler than the arctangent. So the derivative of a sigmoid, let me write it. Right, d to the x of 1 over 1 plus, I'm going to write it like this. This is a sigmoid function. So I'll write it as sig of x. V sig of x to dx happens to be sig of x times 1 minus sig of x. Just a quaint fact of calculus. There's nothing special about this except it's nice. It's simple. If you find another function that looks like a step function and it has an even simpler derivative, use it. It'll be fine. So here's first a calculation of the error function, the error gradient for a single sigmoid unit. So, partial derivative of weight wi with regard to the error. First we write here the definition of the error. It's half of the sum over all the training examples of the squared error of the unit. we can push the partial derivative inside the half and inside the summation. We then take 2 to here times the original times the derivative of the original. The 2 and the half cancel out. This is constant, doesn't depend on the weights. So we're left with a negative derivative of the output on this particular training example with regard to the weight. Now we have to take into account what this output is for a particular sigmoid unit for a particular training example. Remember that the sigmoid unit first does the summation and then it does the sigmoid transfer function. So we can use the chain rule of calculus to break down the derivative of the output with regard to the weight is the derivative of the output with regard to the net times the derivative of the net with regard to the weight. The derivative of the net with regard to the weight is really simple because the net is just a dot product of weight times x. So the derivative of the weight with regard to the net is always just x. And the net with regard to the weight is the derivative of the inner product with regard to the weight. So it just picks up the relevant input, x sub id. The derivative of the output with regard to the net is exactly the derivative of the transfer function. And that's when it's so nice to have this rule that it's just this times 1 minus this. So that's the formula I wrote for you on the board there. So now we put this together with this together with this, and we get the final answer that the error gradient for a single sigmoid unit has this form, which you can write down in your C code or Perl code or whatever, or Java code these days. Right? Very easy. You can just calculate it for your training example. This is if your network consisted of a single sigmoid unit. Now what happens if it consists of a network of sigmoid units? This is when we need to use the recursive definition. And it's called the backpropagation algorithm. And here's how the backpropagation algorithm works. Usually gradient descent is started with some random place, some randomly chosen place in weight space. If you have reason to start from some advantageous place, go ahead and do that. But the algorithm is designed to work from any place. So the first step is you just choose some random weights. Initial the weights to some small random numbers. You want them to be small for reasons we'll discuss later. And you want them to be random because you want to break the symmetry. If all the weights were the same, if they're all 0, actually it will not go anywhere. And now you iterate. And the big loop of iteration is the iteration of gradient descent. Every step in that loop is taking one step in the direction of against the gradient. Within this big loop you have an inner loop that loops over your training examples. For each one of your training examples, you input that training example to the network and compute the network output. This is called a feed-forward step. You put the input here and you propagate it using the current set of weights until you compute the value of the output of the network. Now comes the hard part. You need to calculate the error signal and propagate it backwards. You start with the output unit, k. In the examples I gave you until now, there's only a single output unit, but this works for any number of output units. So you can imagine another output unit here, another one here, and so forth. You calculate the sigma, which is what I call the error signal, based on this formula. And then you work your way back to the previous layer, and you calculate the error signal of each unit in the previous layer recursively based on the error signals of units in higher layers. This is the heart of the recursive calculation of the error signal. The summation here is over all units to which this unit is connected. So if you're here and you're calculating the error signal for this unit, you sum over this and this. You keep doing that all the way down till you get to all the units except the input units. And now the error signal is effectively the main contribution, is the main component of the gradient. The only thing you need to do to turn it into a real gradient is multiply it by the value of the activation level of the unit itself. So the formula you see here is exactly, this is not an approximation, this is exactly this formula. The partial derivative of the error with regard to any weight is equal to the activation level of that unit in that location times, and by the way, this is XWIJ, I'm sorry, I used a single index there for weights because I just said in general index all the weights, but when you do the algorithm, each weight is indexed by two indices, the unit it comes from and the unit it goes to. This together is the negative gradient, and then you multiply it by step size and you get your formula for how to update the weight. So the general form of the backpropagation algorithm, arguably one of the most popular algorithms in the world, at least in the 80s, is you seed the network with random weights, you take one training example at a time, feed it in, propagate the values forward to calculate the value of the output units. Then recursively calculate the error signal using these formulas all the way back. Do that for all your training examples. Add these components together and update your weights and then start all over again. Now you could choose to update your weights after seeing each one training example by itself. That's called incremental gradient descent. Mathematically speaking, it is not exactly gradient descent, because if you take a step doing different considerations different times, you can think about it as doing gradient descent in a different error function. Error function is defined by a single training example, and you keep changing which training example that is. So conceptually it's easier to think about calculating the gradient of all the training examples with a fixed set of weights, adding them together. This gives you the gradient with regard to all the training examples, then taking one step in that direction. Practically, you might get to where you're going faster if you do the incremental version. If you change the weights after each iteration. And most packages will allow you to do it this way or that way. Doing it the right way is called batch mode. Doing it the incremental way is called incremental gradient descent. Questions? Please. Yes, you may end up with a different outcome because of the fact that you're going to get stuck in local minima. So let's say we stick with one of these methods. Let's say the batch mode, which is a true, sort of conceptually correct gradient descent. What will determine where you end up? It's a deterministic algorithm, right? Is it? Somebody else? Please? Your starting point. Where you start will determine where you end. You start at a different random point, you may end up at a different place. Now how good this is all depends on the shape of the error function. If the error function has one or two or three local minima and they're both about equally deep, then okay, sometimes you end up here, sometimes you end up there. But what if the error function, I'll draw it in one dimension, what if it looks like this? Okay, lots and lots and lots of local minima, and the true global minimum, which is much better than all the others, has a very narrow basin of attraction. What are the chances you'll hit here? Very small. It's very small in one dimension, in high dimension it's even smaller. So if the error function has these deep crevices, you're in very bad shape. You're not likely to find them if there's only one of them. If there are many of them all over the place, that's a different story. But if your error surface is very jagged, full of local minima, then gradient descent will not work well. You'll start here, will end here. You start here, you end here. You start here, you end here. So the whole area of gradient descent is a big open area for heuristics, because sometimes you're in a situation where you're not typically going to find a good solution. One problem is you don't know what a good solution is, because until you hit this big hole, you don't know that you can do better. You don't know that there exists a solution that has a lower error. Sometimes you have other reasons to think there might be a good solution, maybe because somebody else's research group got there. There's a lot of work on both speeding up gradient descent and on trying to get over this local minima. I'll give you just a flavor of it. You can change the definition of the error function so that it gets smoothed. So effectively you're introducing a different error function that looks like this. Smooth version of that. And then you do gradient descent in that function, and after you did it for a while and you ended up here, then you reintroduce the correct error function. A slightly different way of doing that is instead of changing the shape of the error function itself, you change the rule of moving the space. Imagine that normal gradient descent, you have a ball that just rolls down the gradient, the error gradient, until it gets to a point where it rests. Okay? That's okay if the error surface is good. But what if the error surface looks like this? Then you put a ball here, and remember the ball has no inertia, so it'll just roll down to here. So what do? You use a ball that has some bounciness to it. You let it bounce up and down. That corresponds in searching the space to allowing yourself to go against the gradient sometimes. So you deliberately introduce perhaps random changes in the weight, in your place in the weight space, that occasionally go against the gradient. Namely, will pull your network towards a point in weight space that has more error. You allow that on purpose because you're trying to get it to kind of bounce up and down. And the way you end up at the lower place is very interesting. You start with a very bouncy ball that allows itself to bounce a lot. And you let it bounce many, many times. And after a long time, you reduce the bounciness a little bit. You now allow it to bounce only this high. And then after a long, long time, you reduce the bounciness some more. And you reduce it more and more and more and more. In the end, you allow it to move very little. And what happens is that if you do it slowly enough, you're guaranteed to find the global minimum. And the reason is, there will be a time when the ball is allowed to bounce, let's say, this much. And if you wait there long enough, it will eventually find this hole and go down and won't be able to come out. The trick is, of course, that nobody tells you how long you have to wait in each bounce level. And the proof is only that if you do it slowly enough, it is guaranteed. But enough is not, infinitesimally slowly. Some of you may see this as familiar. It goes by the name of simulated annealing. This is called simulated annealing. It's a technique that comes from physics. Annealing comes from physics. Simulated annealing is the computational simulation of an annealing process. And reducing the bounciness corresponds to what's called a cooling schedule. The bounciness of the ball corresponds to the energy level of a system. And you start with high energy level, which allows it to move across into unfavorable situations temporarily so it can bounce down. It allows it to get over humps. And then you cool it gradually. This is just one of the most famous ways of trying to handle this problem of searching a space that has lots of local minima. There are other ways of doing that. The simplest way is to try to start in many different places and see what happens. Now, I mentioned in the 80s the paper that made backpropagation popular showed that there were lots of interesting examples where this was not a problem. And it's true. But there are also lots and lots of problems where it is a problem. So one of the most famous ones is speech recognition. In speech recognition we use hidden Markov models, which we will study in this class. We actually use hidden Markov models in many other areas of AI, but maybe they're most famous in speech recognition. Hidden Markov models have a learning algorithm that effectively uses gradient descent in a very high dimensional space, and it does get stuck in local minima all the time. We don't know how to find the best possible hidden Markov model parameters, where we know that we get stuck nowhere near the potential of hidden Markov models. And we don't know what to do about it. Questions? Read all these restrictions. Neural networks and backpropagation are incredibly powerful. They can learn natural categories very quickly and very nicely, even if these categories are not very nicely linearly separable. I'll give you one example from speech. The way we recognize vowels, we as people and also machines recognize vowels, is by doing a Fourier transform on the wave signal and then observing where most of the energy of the wave signal is concentrated. Typically, if you look at something called a spectrogram, which is a Fourier transform of a speech signal, you will find that the energy is concentrated in a few places. In all of human speech, it's always concentrated in a few places. If it's not concentrated in a few places, it's typically not human speech, it's some kind of noise. And these places where it's concentrated are called formants. The first three formants pretty much define for the human ear what a vowel is. If you gave me the three formants, I could tell you what a vowel is. But the relationship is not so simple. In fact, you can even do it with two formants most of the time. One of the reasons telephone speech is not so clear is because it chops off the third formant in many cases. But two formants is usually enough. And here's an example of a real-world, non-trivial problem. And this is the problem of classifying vowels based on the first two formants. So the representation here is x-axis is F1, the first formant in hertz, that's the unit of frequency, and F2 is the second formant, and every point here is one recorded vowel that somebody said, a, u, e, whatever. The symbols are the different vowels from English. Not being a native speaker of English, I can't replicate them exactly, but you have head, hid, hod, had, hod, heard, heed, hud, hood, and hood. It's my best attempt at it. My native language has far fewer vowels, so 3 or 4 is all I can do. And you can see that the vowels in this space are pretty much separated. You can see that they have their own neighborhoods. But the interesting thing is the decision surfaces, the decision boundaries are not linear. They have these funny shapes, these cells. So a human looking at it could draw circles around them like we did there. But to a machine it's not easy to find the rule, and a network of linear units would never do it. And a decision tree would have a hard time too. Because if these lines were horizontal and vertical, the decision tree would do well. But because these lines are diagonal, you have to tell the decision tree, take this formant times 0.3 and this formant times 1.7 and combine them, right, to form the slope. And how do you know to do that? So decision tree will not do so well here. Neural network did beautifully here. This is the topology of the network that was used for it. You have just two continuous inputs. You have about 10 outputs, and you have a single intermediate layer. And the network was trained using the backpropagation algorithm and these training examples. And after it was trained and reduced error, I don't know if it reduced it to 0 or to close to 0, it was used to draw these boundaries by going over every point in this space and calculating what the output is. I should tell you that how do you use a network to calculate, to classify into 10 different outputs? The answer is By convention, you decide that whichever one of these output has the highest activation level is the winner. Okay? This is a standard way of using a network that calculates a number or a set of numbers to make classification. So this is what was done here. You can see what the network was able to learn. It was able to learn these idiosyncratic decision surfaces. This is a hallmark of neural networks. You don't have to explain to them things in symbols. You just throw the data at them and they naturally come up with these ways of carving the space and saying this part has this category, this part has that category. There are literally thousands of different problems that neural networks were thrown at and did surprisingly well. Next time I'll tell you of some caveats, when they don't do so well. But this should be enough for you to do your homework, I think. And if it's not, do whatever you can and write to me about the rest. Okay? Thank you.